Here we are at our last podcast of Unit 11, and we're talking about titrations, these labs that we're going to be trying to do coming up in the next couple of classes. And we are filling out pages 12 through 14. Don't let that panic you, though. This really shouldn't be too tough or complicated. We're going to start with some definitions and kind of notes in the margins here, and then we are going to draw a few graphs, which is really most of the space we're going to take up. And then we will finish with a few calculations that are related to the stuff that we were starting to talk about and kind of having to set the stage for here up front. But the calculations themselves aren't really that complicated. So don't think just because they need 2 pages of lead up to them that they're going to be impossible, because I think you'll be pleased with how easy and straightforward they are. So let's start talking about titrations. You'll notice that the word titration and burette are not in your notes. You're welcome to add them if you'd like. I just want to make sure that I explain to you what is a titration before we get into all of the details and complicated stuff about titrations. So write them, don't write them, it is up to you. Just make sure you do write down unknown, standard, and indicator when we get there. So what is a titration? Well, it's a very carefully controlled reaction where we use a standard solution, something we know the information about, something that's a pretty specific molarity, to determine the properties of an unknown solution generally. So we're going to be doing some calculations here and using what we know about one substance and solution to convert into getting us information about another solution. So our unknown is the substance we're trying to investigate. And in this setup over here, when we're doing a titration, this is what we're going to have on our lab table. And the thing that we're investigating is going to go in the flask. And we're going to be reacting it and adding stuff to it to learn more information about it. The standard solution is going to go into the burette, which is this tall thing here with that light green solution. And that's what a burette is, a tall, thin measuring tube. And the thing that's special about it is that 0 is at the top of the tube. So what we do when we're doing a titration, there's a little knob down here that we turn. And when we turn it, it's going to start letting out a little bit of that solution. And we can tell how much solution has come out based on how far down it goes. So this measures from 0 at the top because it's measuring how much stuff we've poured out of this device. In a graduated cylinder, normally we are pouring stuff into our graduated cylinder, and so that's filling it up. So 0 starts at the bottom, and then it fills up to a certain level for us to read off. So the burette is made to dispense a certain amount of stuff into another container and measure how much stuff is poured out. And the other thing that's important for our titrations is an indicator. And an indicator is just a special chemical that changes color at specific pH ranges. So we'll be able to tell when we get to that pH by telling when our indicator has changed color. And we'll come and look at some indicator examples a little bit later and all the pretty colors that they can turn. But the whole point of this is to keep adding our acid or base, whatever our standard is, into the unknown until we see that color change. And that color is going to generally change when our acid and our base have neutralized each other. And when we are neutralized, we've reached the end point. We're done as soon as that color changes, so that's the end point sometimes. But really what we should realize about it is that it is also called the equivalence point, or it's mainly called the equivalence point, because once we get to that point, once our acid and our base have neutralized each other and canceled each other out perfectly, then the amount of acid that we have is equal to the amount of base. And the way we quantify and calculate amounts is with moles. So when we call this an equivalence point, it's because our moles of our acid and moles of our base are equal to each other. So this is what we're going to come back to and use to help us set up and solve all of our calculations there on page 14. We have a little bit more to talk about here before we get there. So put this to the back of your mind for a moment. Over in the left margin, it asks, how does the pH change during a titration? So we want to answer that real quick before we get into the graph so we understand what we're drawing there. So there are two different options for our acid-base titrations based on whether we want to be studying the acid or the base. So if we're adding a base from the burette into an acid that's in the Erlenmeyer flask, when we're measuring and observing this reaction, we're going to be observing the flask. So when we think about how the pH is changing, it's going to be starting at the pH of the stuff that's in the flask and then changing to be a little bit more like what's in the burette. So if we think about the pH of an acid, that's going to be less than 7, and no matter what my base is, its pH is going to be greater than 7. So if I'm starting with an acid and going to a base, then my pH is going to increase. If I start with the base in my Erlenmeyer flask, then that means I'm starting at a pH that's bigger than 7, and then I'm adding acid to that until we get to that equivalence point, and that is going to be bringing our pH down. From our base's pH, adding more and more acid will make it more acidic, lower pH. So when we're drawing those graphs, we're actually going to draw two types of graphs for each of those spaces, one where it's increasing, one where it's decreasing, but we'll get to that in a moment. But every single reaction is going to have the pH change in a predictable way, and we're going to be able to find the equivalence point using our indicator if we can predict about where that pH is going to change. So this is a list of our indicators, just for reference. There's no place that you need to write this down, but I just wanted to give you an idea of how many indicators there really are out there and all of the different pHs that they change their color at. The three most common ones that we're going to see are methyl orange, bromothymol blue, and phenolphthalein. And if you look, phenolphthalein is probably what we're going to be starting with. So that's going to be starting at clear around pH 8 and changing to pink as we get to kind of pH 9 and higher. So that's what this is kind of showing you, all the different colors they change and where that change starts to happen. This will still be clear all the way down on the pH scale and probably be pink and even pinker as we go up on the pH scale, but that's where the change happens. So if you can figure out where your acid and base are going to be equivalent, what pH to expect them to be equivalent at, then you can choose the correct indicator for that pH. So that's what we're going to get into now, is specifically where can we expect that equivalence point to be. And really what we need to think about it mentally as is a tug of war on the pH scale. Whoever's stronger is going to be able to pull the equivalence point onto their side of the pH scale. And depending on the difference in that strength, then it might get pulled farther or less far. So, as we're looking at each of these next three scenarios, think to yourself, who would win? Well, in this first situation, if my acid is strong and my base is strong, then there's not really a good way to tell who would win. And honestly, neither of them might win. They just might be sitting there tugging on that tug of war for a while without any movement. So what that tells us is that if neither of them is winning, if they're both strong, then our equivalence point isn't going to be on the acid side or the base side. It's going to sit there right in between them at 7. So we're going to draw two graphs here. And the most important thing, we just want a rough pH scale on the y-axis. Technically across the x-axis we could have a couple different units, whether time or volume added. But what we're going to do is just draw two rough graphs with this dot perfectly in the center. And we're going to label this first one, and I'll use an actual readable color here, base added and acid added. So that's how we're going to kind of treat this x-axis here, is the amount of our standard that was added, and these two different graphs are for these two different situations. Here I'm adding a base to an acid. Here I'm adding an acid. We can assume that there's a base in that flask. So if we think about where our pH is going to be on this graph, if I'm starting with an acid in this first graph and adding more and more base, then I expect my pH to start low at the very beginning when I haven't added very much base. And when I've added almost all of the base, then it's going to be super high. Now, this isn't going to be a straight line graph. What actually happens is that these pH changes start off kind of slow, and then they're going to shoot up, and then they're going to be kind of slow again. So we have this kind of S-shaped graph here. And normally, if you were trying to find the equivalence point instead of starting with that point, you'd graph all of your pH data that you're measuring throughout this reaction and then find the midpoint and look at where that pH is. So this lies right about 7, but that's what we were aiming for. Now this other graph, the midpoint is still going to be at 7, but if we think about it, we're adding an acid to a base that's already in that flask. So we're going to be starting with a big pH and coming down to a low pH. So this graph is going to be kind of flipped this way. So just a rough graph showing that equivalence point still. You can barely see mine, but it's important that we do see that point there right in the middle of that vertical section, and the fact that that does line up perfectly with 7. So go ahead and draw 2 graphs on the next couple of slides. I'm just going to draw 1 each time, and then you can kind of do the other one if you want to see it, or you might just draw 1 and understand that they do kind of flip depending on what's being added. So let's go ahead and look at that next page where we have our strong acid, weak base titration happening, and thinking about where we would expect the equivalence point here. Well, if my acid is strong and my base is weak, then the acid is going to be winning the tug of war, and so that's going to pull our equivalence point onto the acid side of the pH scale, below 7. So as we start to draw our graph, we need to make sure that we're aiming for the middle of our S-shaped thing to be here below 7. And I don't care whether it's there or even lower, but I'm going to imagine that we're starting with an acid and base added. So we're going to start low and end high, but if our base is weak, it's probably not going to end quite as high. So this is going to, yeah, that works. Enough. So look a little bit like this, with that equivalence point, middle of my S-curve, below 7. And flipping that around would just kind of come down this way with the other graph. Then if we go to our strong base mixed with the weak acid, this time the base is winning our tug of war, which means it's going to pull our equivalence point over 7. So in our graph, we need to aim for the center of that F shape to be above 7, and I'm still going to say that I'm starting with an acid and adding base to it. So I'm still starting low, but if my acid is a weak acid, it's probably going to be a little closer to 7 than 1. And then I'm going to follow that, well, best I can. Kind of up and over. That works. And that is our weak acid, strong base titration curve, or at least what we would expect that titration curve to look like. So you're not going to have a ton of graph questions, but we do need to be able to reason through where that equivalence point would be at the very least, and just think of it like a tug of war. So now we're on that page 14, and this is that idea that I said that we were going to come back to. The idea that at that equivalence point, moles of acid are equal to moles of base. Now, what we're actually going to do is use the molarity equation to alter this a little bit. Because moles aren't actually measurable in the lab, what we are going to see and measure is either the molarity of our acid or base or the volume of the acid or base that's used. So if we solve that molarity equation for moles, then we can plug in molarity times volume on the acid and base side, and we get something that looks a whole lot like the dilution equation, actually, except we've got A and B instead of 1 and 2. But the idea is the same. If we know the molarity and volume of either our acid or base, we can use it to help find the molarity or volume of the other one, as long as we know one of those two values. And the easiest way to solve these problems is still probably to think about, what am I looking for? For example, like if I'm looking for volume of base, then I'm going to be doing the opposite side calculation, so MA times VA, and then going to be dividing by the thing I'm looking for's neighbor, MB. And that's going to get us our answer. So these next few calculations are actually going to go pretty quick, and you might be able to work them out without my help. So let's go ahead and look at them anyway. It says that a 15.5 milliliter sample of a 0.215 molar potassium hydroxide solution. So pause. As soon as I saw that was potassium hydroxide there, that's our base. And I already had two numbers given to me. This is my volume of my base, and this is the molarity of my base. So I am 2/3 of the way there. So it says that much stuff is required 31.2 milliliters of our acid in a titration. So here is the volume of my acid. And it asks us to calculate the molarity of that hydrobromic acid solution. So we're looking for the molarity of our acid. Now technically, if we did sit there and rearrange the equation with our algebra skills, we'd get the fact that the molarity of the base times the volume of the base divided by the volume of our acid is going to get us that answer. But once again, we're just going to be finding the thing that we have two numbers for and multiplying them together. So it doesn't even matter what order they're going to be in. I'm just going to write them in the order that we find them. That is a decimal point there, 15.5, 0.215, and then divide it by the other acid number. Now, in case you're wondering, no, it does not matter that these are milliliters in the slightest. Just like with the dilution problem, it does not matter. So, no milliliter to liter conversions in this unit. Now, multiplying those numbers on top, dividing by the bottom, we get 0.10681. I'm sure it keeps going, but here we want to keep 3 sig figs. So I want to keep the 0.106 part, but the next number is an 8. So that's going to round our 6 up to a 7. So my answer here is 0.107 molar acid. In our next problem, got a little bit more writing, not much. As we're reading through, it says by titration, I have this volume of an acid that neutralized this volume, I assume of my base, lithium hydroxide. And it gives me the molarity of my base again, too. So it's asking me to find the molarity of my acid. So I'm not going to bother rearranging my equation, partially because it's the same as before. I'm still solving for molarity of acid. But because I'm just going to take those two numbers that both go to the same solution. So once again, it's the base, 165, two base numbers divided by the one acid number that I have. Do all that multiplying and dividing. 25688. And here 3 sig figs all around again. So I want to keep the 0.0256, but once again the 6 is going to round up to a 7. So 0.0257 molar. Done. This next one does not ask me to solve for the molarity of acid. In fact, it asks for the opposite, the volume of the base. But I don't care about that quite yet. I know I'm trying to find the milliliters of volume, I have this molarity. That's when I see it's potassium hydroxide. So both of these are the base. This just happens to be what I'm looking for. So it wants me to figure out how much of that base is needed to neutralize this volume of my acid. So, not going to rearrange the equation. I'm going to focus on the simple things. What I know is that the opposite stuff, the acid numbers that I have both of, get multiplied together, and then I'm going to divide by the only number I've got for my base. When I do that, this answer comes out to being 45, and that works just fine for me. No rounding needed, because this 2 sig figs here, that 3.0, means that 2 sig figs in my answer is just fine. Just make sure that these volume units match our other volume units. These were milliliters before. So, that's it.